Alright, example 13.3 says the following equations and graphs do not represent polynomial functions. Explain why these are not polynomial functions. So let's start with the equations. Looking at the equations, let's look at the first one. F of x equals negative x cubed plus 2 square roots of x minus 5. Now, if I was to try to think of this as a polynomial, I know it's not, just play with me here. If I was to think of it as a polynomial, then I would probably identify the negative x to the third as my leading term. That would lead me to believe that the degree of this polynomial is 3. So let me think back to the definition for degree 3. For a degree 3 polynomial, it would have to be a3x cubed plus a2x squared plus a1x plus a0, which I have part of this structure here, but I don't have all of this structure here, which is okay. You don't have to have all of it, but you also can't have stuff that's extra that's not supposed to be there. So these are the only 4 terms that you would be allowed to have in a degree 3 type polynomial. You can have a constant term, we've got that. You could have a x term, which we don't have, which is fine, you don't have to. We could have an x squared term, we don't, which is fine. But you would have to have the x cubed term in order for it to be degree 3. Like you can't be without that. So, and we do have that. So the concern here would then be this extra term, 2 square roots of x. So going back to section 2, I know it's been a while since you've looked at section 2, but in section 2 we had talked about the square root of x, or the square root function. So here we're just looking at the expression square root of x, because in section 2 we mentioned that the square root of x is the same as x to the 1/2 power. So when we're dealing with a polynomial, we had emphasized with the definition that we're only looking for natural numbers when we're looking at the degree and also for the exponents within the polynomial structure. Clearly 1/2 does not count as a natural number. So this is the reason why the equation here for A does not qualify as being a polynomial. It's because one of the exponents is not a natural number. So I'll let you pause the video, write something down to explain what we just discussed. Let's go on to part B. G of x equals pi times x to the 4 plus 12x squared plus 3 times x to the negative 1. So here I'm looking at pi times x to the 4 as being my leading term. That would indicate that I should have a degree 4 polynomial. And I also noticed that my coefficient here is pi, which is perfectly fine. Pi is a real number, and all of my coefficients are supposed to be real numbers. So pi is not the issue here. The issue is this last term. In this last term, we have an exponent of negative 1. But per the previous example, part A, we were discussing that the exponents need to be natural numbers. Well, negative 1 is not a natural number. It's an integer, but it doesn't qualify as being a natural number. So the fact that we have x to the negative 1, that's the reason why we have to disqualify this as being a polynomial. This is going to end up being something else. So again, you can pause the video and write down an explanation for why g of x is not a polynomial. So now let's move on to h of x. So with h of x, we have something interesting. We have a polynomial, degree 2, and we also have a linear, degree 1 polynomial. And these two polynomials are being divided by each other. Nowhere in our definition of a single polynomial function does it say dividing. Now, there are other operations that we can do, like addition, and we could still get a polynomial. Now the reason why addition is okay is because you just combine like terms. For example, if I was to say x squared minus 2x plus 1 plus x plus 3. Those are each polynomials. And when I add them together by combining like terms, I would have x squared minus x plus 4, which on its own is still a polynomial. But with division, we can't actually do that division of x plus 3 into x squared minus 2x plus 1. And so this ends up creating a problem for that polynomial structure, because all we can really do is think of this as just two separate polynomials being divided. That's the reason why this doesn't qualify as being a polynomial. Now, as a preview of coming attractions, this does have a special name. This is known as a rational function. We will do a much closer look at the rational function coming up after our study of polynomials. Part D is going to look at a graph of a function, and the problem here is continuity. Now there are continuous aspects to this, so I don't want you just to say it's not continuous, because that would be false. It is continuous from here to here, and it's continuous from here to here. But it's not possible for me to be able to draw the entire picture with just one fluid pen stroke. And that's because there is a gap here at -3. So because of the gap here at -3, this is not continuous everywhere. So I'll go ahead and write that for us. It is not continuous everywhere. And that is the reason why this doesn't qualify as being a polynomial. The next picture, part E, is the graph of G. Now this is not the same G that's up here in the equations. This is different. But what we'll notice is really the same argument that we had for part D, where I can draw one piece continuously, one fluid pen stroke. I can draw this other piece in the same way, but I can't draw the two together with one pen stroke. And that's because there's this gap here located at -3 again. So this is also going to be not a polynomial for the exact same reason. It is not continuous everywhere. Part F, however, can be drawn with one continuous pen stroke. I can go all the way from the left to the right, and I can make it all happen because whatever pieces I have here are connected. So continuity is not the concern. The concern here then would have to be smoothness. There are two places where we have not smooth transitions. That would be right here at -3, -2, and then also at 2, 3. These are known as cusps. I have two cusps in this graph. Now I have 3 transition points. I have another transition point here at 3, 2, whenever we're going from decreasing to increasing. I've got a vertex there. So I actually have 3 vertices here. But 2 out of the 3 vertices do not have a smooth transition, and so they prevent us from having a polynomial structure in terms of the graph, and so this is not smooth, and that would be the reason why these are this one in particular is not a polynomial function.